Okay, well, thank you for joining us and welcome to today's research webinar. This is on insights from the new end-of-life EV battery policy simulator. My name is Sarah Schremer. I'm the policy director for the National Center for Sustainable Transportation. Housed at the Institute of Transportation Studies at UC Davis, the National Center for Sustainable Transportation, or NCST, is part of the University Transportation Center's program administered by the US DOT. The NCST provides national leadership in advancing environmentally sustainable transportation through cutting-edge research, direct policy engagement, and education of our future leaders. Our national, went too far. Our national center works in partnership with a consortium of 7 universities: CSU Long Beach, Georgia Tech, Texas Southern, UC Riverside, the University of Southern California, and the University of Vermont. And with that, it's my pleasure to introduce today's speaker. Joining us is Dr. Alissa Kendall. She is a professor of civil and environmental engineering at the University of California, Davis. Her research interests focus on evaluating the material, energy, and waste flows generated by engineered systems and refining and enhancing the methods used to evaluate their impacts, with a focus on transportation systems and climate change. Her recent research integrates economic, environmental, and social factors in a mixed methods approach in an effort to shape robust policies for lithium-ion battery end-of-life management. We will be recording this webinar, and the recording will be available on our website along with the presentation slides in the coming days. If you have any technical issues, please let us know in the chat and we will do our best to assist you. During the presentation, please use the Q&A feature that you can find via the little button at the bottom of your Zoom window to type in your questions. We will have plenty of time at the end to respond to those questions live after Dr. Kendall has finished presenting. And lastly, please pay attention to the chat because you'll see a quick survey at the end of the webinar for you to share your thoughts with us on today's presentation and ideas for future topics as well. So with that, I think I will go ahead and pass it over to Dr. Alissa Kendall. Thank you.
Well, thanks so much, Sarah. Thanks for the introduction. And make sure you can see my screen here. And I'm going to be talking about results or outcomes from some work that my research group did, funded by the NCST, to develop a end-of-life EV battery kind of policy simulator. This is a kind of a dynamic systems model where we can test out different ideas to see how they perform. I really want to emphasize the contributions of the 2 graduate students who were funded on this project, Meg Slattery and Dr. Jessica Dunn. You'll see their names throughout here as lead authors on a bunch of the papers that I'll be presenting on, and they are true experts and deserve most of the credit. So with that, I want to acknowledge the funding. This is an NCST project funded by the NCST on the project I've listed here. I also use NCST work that was funded by the NCST in a previous project as well, and I wanted to acknowledge that that work as well. It sort of set the stage for the focus of this talk. Most of the work presented is drawn from a number of papers, and I've listed them here. And I think you'll be able to see a few of those resources in the chat as well. Some of the work is still under review and is not yet available in a published format. Okay, with those acknowledgements over, we can dive into the actual research. So I'm going to start by talking about electric vehicles in general and electric vehicle batteries in particular. And of course, the first question is, why do we need electric vehicles? We need them because they're crucial in basically every decarbonization strategy that's out there for the transport sector. And in particular, in a car-dependent place like the United States, we are even more dependent on electric vehicles to deliver lower carbon transportation. And that's great, but there are a number of challenges to electric vehicles. One of them is lithium-ion batteries, or LIBs. These are what we call traction batteries. They provide the power and store the energy that we need to move our cars and our trucks. And before electric vehicles started using lithium-ion batteries, they basically were small batteries we used in our consumer electronics, right? To to basically deliver on electric vehicle or vehicle electrification, we've needed to build new supply chains and massively expand production of these batteries. And so there are a lot of concerns and impacts around that. Most of you have probably heard about critical battery materials, so the risk that we're going to run out of these materials. And I don't mean run out in like a geologic sense. I mean that we're not going to have enough available when we need it to meet our targets for electrification. But all of this new production actually has implications for waste streams that we haven't necessarily planned for or faced in the past. And I don't just mean waste streams generated at mining or refining sites, but the batteries themselves, which will get used and eventually become spent batteries or that need management. We're kind of fortunate in that these batteries last a long time, right? We put them in a vehicle, they last 8 to 15 years, let's say. We can anticipate what likely futures look like and make policy and technology choices that can minimize negative outcomes and hopefully maximize benefits to society. One challenge we have is that end of life of batteries hasn't really been much of a focus in the past. It's frequently overlooked or treated in very simple ways in environmental and cost assessments of electric vehicles or lithium-ion batteries. How we manage these batteries is actually really important, though. The way that we manage them can determine, for example, how much new material we need to make batteries in the future. For example, if we're good at recycling and recovering materials, maybe we can mine less. If we're good at repurposing and reusing batteries, maybe we can create fewer batteries. All of these have implications for the total impacts associated with electrifying our vehicle fleet. The other issue with battery management at end of life is that batteries actually present some health and safety concerns, whether it's the fact that they are high voltage devices that often arrive at treatment facilities still with some power in them, or because they actually have a risk of fire. And these fires happen unexpectedly. It's not like a spark sets them off. When batteries, lithium-ion batteries age or are damaged, the risk of these kinds of fires increases and can present a challenge for health and safety as well. So those some of the needs we have, or the rationale we need of why we need to focus on batteries and their end of life. But to really think about the problem, we have to start at the beginning. We have to start with demand for lithium-ion batteries, because we need to understand, well, how many batteries are going to be put out there and when are they going to retire? Once we know that, we can think about more other issues like what are the potential management options and what are the risks of not managing these end-of-life batteries properly, and what are the best solutions for managing them. So here I'm presenting some earlier work thinking about EV demand and sales projections and how that would lead, what that means for battery retirements in the future. So in this work, we looked at a number of different global regions, and in those global regions, we projected out to 2040 what vehicle adoption might look like. I'm just showing you a subset of the scenarios that were explored, but the key thing I want you to see here, the pink is the US, and the orange is Europe, and the purple, the green here is China, the purple is everyone else. And what we can see is that you have this demand for electric vehicles, and then you have retirements, and it's a lagging process, right? We have a big lag between when a vehicle goes on the road and when those battery retirements will begin. We are really early in battery retirements, right? We have not seen a lot of batteries retire. One other observation you might make here is that the US seems to be a little higher on battery retirements, as this is in terms of gigawatt hours or battery capacity retired. The US uses bigger batteries than other places. So the number of EVs means is not a perfect mapping to this retired gigawatt hours. So all of these retired batteries could either be an opportunity or a big risk or some combination of both. What can we do with batteries when they retire from an electric vehicle? We could reuse them with or without repair. Usually we probably need to repair them. They were probably taken out of a vehicle for some reason, but there may be some cases where you can directly reuse them in another electric vehicle, and that's one option. We can repurpose them. This is something we actually think more about, that we take an electric vehicle out of a battery out of an electric vehicle when its state of health is something around 80%, maybe a little lower. a battery in an electric vehicle is being asked to do a lot. There's an enormous demand for power, and there's a really high demand for energy storage capacity. One of these batteries that no longer functions in a vehicle is still a really good battery for lower demand applications, for example, in stationary storage. And I'm showing you a picture from a California company, B2U, that has repurposed a number of different batteries from a number of different vehicle models, and they're using them to support a utility scale solar installation so that they can store electricity during peak production of electricity and release that electricity during peak demand. And that's one potential application for repurposing. And then finally, we can recycle these batteries. When we recycle, we typically are aiming to recover the constituent materials that are valuable in the battery. And I'm showing you here a picture of black mass. This is an intermediate recycling product that happens when we hydrometallurgically recycle batteries. Okay, so these are our options of what we could do with retired EV batteries, other than the bad options, by the way, other than stockpiling them somewhere or sticking them in a landfill or not managing them properly. So what happens to EVs and EV batteries at their end of life? This is a slide that Meg Slattery put together, who's been the lead researcher on understanding the end of life, the EV battery end of life network and industry and process. We might imagine that somehow these batteries are all managed, for example, at dealerships that OEMs own. OEMs are original equipment manufacturers. They're the brands that we recognize when we buy a vehicle. You know, and there's definitely a model for this where an owner of a vehicle takes their vehicle into a dealership. The dealership removes a battery for one reason or another, or takes a vehicle, and then they manage that battery appropriately. But in reality, we have a much more complicated and kind of messy end of life system for vehicles. And I don't want to imply that our vehicle end of life industries aren't good at what they do, just that there are a lot of options for what can happen to batteries. Shown here is, you know, like essentially a vehicle scrapyard. We have vehicles that get exported to other countries once they're used in the US. We have, you know, hobbyists who might try to take a battery out of a vehicle and repurpose it for their own uses. There's just a lot that can happen out there for what actually happens to batteries once they've been retired from an electric vehicle. One thing that emerged from this research is the fact that there hasn't been sort of an authoritative mapping or charting of the EV battery end of life process and the industries involved. So we initially undertook a literature review to understand how EV battery end of life had been modeled or sort of understood mostly in academic research around environmental and cost assessments. And I'll briefly cover some results there. The big headline is really about the work that Meg led, doing qualitative research via expert elicitation to interview lots of stakeholders in this end of life industrial ecosystem to better understand what was happening with batteries and understand what they saw as potential issues and opportunities. So in this literature review, maybe the headline is that it turns out transport costs are really important. And, you know, a lot of folks may know that recycling, there's a cost to recycling. People wonder why it's not basically a better economic deal. And for large lithium-ion batteries, a big issue is the cost of transport. So the cost of transport could be nearly half of the cost of recycling. And the other headline from this study was that lots of studies either omitted this stage in terms of the cost or environmental impacts associated with EV LIBs or lithium-ion batteries, or just treated it very simplistically. So that's part of what inspired the need to do this research. So we interviewed 28 stakeholders from across the battery end-of-life industries. So we have battery recyclers and reusers, for example, folks involved in the OEM network, folks involved in collection and storage, and a large group of people involved in vehicle afterlife industries. These folks have been working with end-of-life vehicles for a long time, but of course, most of what they work with are gasoline vehicles. Over the past 10 or 15 years, they increasingly saw hybrid vehicles and are now starting to interact with end-of-life electric vehicles as well. One of the key results from this work was something of a consensus chart or mapping of the pathway for retired EV batteries and retired electric vehicles in general. There's a lot going on here that we don't have time to cover, but the color of the boxes here refer to which stakeholders or industry sectors are involved in the end-of-life pathway. So in light green here, you see the OEM network that includes vehicle manufacturers, dealerships, and some refurbishment and remanufacture of batteries. You have the independent vehicle network shown in a darker green. I think of these as largely incumbent industries that have long been working with gasoline vehicles and are now faced increasingly with batteries from electric vehicles. And then you have metal refining and mining and scrap recycling. So this is sort of how traditional or recycling has happened for vehicles, where metals like steel and aluminum are going to be recovered, and copper. And then you have industries that are more focused on batteries in particular. So these are kind of new industries. They're not these older industries that are facing a change of EVs, but they're emerging as new. And these would include repurposers, battery repurposers, dedicated collection and sorting facilities, and then of course battery recyclers shown around here. And in theory, we can close the loop by recycling batteries and putting that recovered material back into new batteries, which is what's shown here, sort of a circular approach. So another key result from this work was insights garnered from stakeholders. And so some themes emerged from these interviews. This included critical issues that a number of sectors identified around safety, the cost and challenge of transporting end-of-life batteries, and access to information. And the kind of information we're talking about here is information about the actual battery. What's the chemistry or composition of that battery? What's the state of health or remaining capacity in that battery, etc. There was also a strong commitment to creating closed-loop value chains, and maybe that motivating novel relationships or partnerships between industries, for example, between recyclers and producers. Some other insights around the challenge that recyclers and repurposers are facing in the short term with respect to access to end-of-life batteries. So you might remember that curve I showed, and I said, we're right here. There's not that many end-of-life batteries batteries retiring from EVs right now. If you're an industry trying to get started, like the repurposing industry, or you're trying to grow, commercial scale, industrial scale facilities for recycling, for example, you need more batteries than what are out there right now. So you're sort of waiting for the stream of batteries to arrive. So there's some competition between these two sectors. Compared to other countries, one thing that folks noted, that we don't really have a mechanism, a policy or regulation, for example, in place to ensure batteries are collected and recycled. It is a purely market-driven system right now. Kind of related to that, there's no tracking system for these large batteries, meaning that we don't really have a lot of data to understand what's actually happening on end-of-life lithium-ion battery management. And then related again to that first problem of no mechanism to ensuring batteries are going to be collected and recycling, we have a system that depends on the economics of reuse and recycling. And so there is this risk that when the economics don't work out, we have stranded batteries or lost opportunities to recover the materials in batteries because of the limitations on cost. Okay, so maybe one of the key headlines there at the end is that we really don't have any policies directed towards managing end-of-life batteries. We have some laws that sort of direct how things are done, like that end-of-life batteries are hazardous waste, so they have to be transported a certain way, that there are often landfill bans. So if you're going to dispose of an end-of-life lithium-ion battery, it has to be in the appropriate kind of landfill, like a hazardous waste facility. But we don't really have policy in place to really manage end-of-life batteries. So the work that I'm going to follow up, so I've presented some of the qualitative work we've done to better understand how things are and what are some of the challenges that experts or stakeholders in the industry see in the future. And now I'm going to present a bit on some of the quantitative assessment that we've done using life cycle assessment, material flow analysis, and some cost analysis to test out different management strategies and policies, and hopefully guide future policy development or encourage policy development in the US. So I'm going to start with talking about recycling. I think a lot of folks are familiar with the idea of circularity or a circular economy, and a lot of times we envision circularity being achieved by recycling what we're using, right? So if we can recycle everything at really high efficiency rates, we don't need to dig up new materials from the ground, for example. And one question we could ask is how much can recycling really deliver? And maybe I think it was about last year, I did an interview with a journalist, and the journalist was really emphatic about how, you know, it wasn't right that we had to dig up new materials. Can't we just recycle things? And I said, yeah, of course, that's great. But you can't recycle something if it's not made yet, right? And right now we're in a period of extensive growth in demand. So the question is when and how much of our future demand can be met by recycling, because our current demand certainly cannot be. So to understand that, we have to know what goes into a battery, right? And this is a kind of cool like diagram for the average lithium-ion battery in 2020, showing what has gone into it. I want to start by pointing something out that I think is often not, I don't know, that is often a surprise to people, but because of the name, but lithium is down here. It's only 3.2% of the battery. We have a lot of other stuff going in there. We've got nickel and manganese and cobalt, and some iron. These are all going into the cathode. And then we have other materials like graphite, for example, which is used commonly used in anodes in lithium-ion batteries. And so we have a lot of other materials that aren't lithium in here. The materials that have probably received the most attention in sort of in research and in popular culture are cobalt and nickel. Cobalt is particularly problematic because of environmental, social, and governance issues associated with its extraction and refining. More than 70% comes from the Democratic Republic of the Congo, which has a very long history of human rights violations and unsafe working conditions and unfair working conditions for those who are mining cobalt. Nickel is also a very environmentally intensive material and costly, and so cobalt and nickel in particular have received a lot of attention because of their cost, and for cobalt's case, some very clear issues around social impacts and governance. We often talk about lithium-ion batteries based on their cathode materials. So lithium-ion battery is just a category. Within lithium-ion battery, within that category, we have lots of different chemistries. And one thing that's been happening over time is changing chemistries. So the cathode is, like I said, usually determines how we talk about the battery. So this is NMC 111, if you've ever heard of that. It's nickel, manganese, cobalt. And these show up in equal proportions in the cathode, which is why it's called 111. We have seen a trend towards trying to design out some of these most problematic materials. So for example, NMC 811 does a good job of really reducing cobalt content in these batteries. Remember, cobalt is this problematic material. We've also seen a trend towards moving away from chemistries that include nickel and cobalt. For example, LFP, lithium iron phosphate, which includes none of these nickel, manganese, or cobalt materials. I'm telling you this because if you think about circularity, if the products you're making and retiring are changing over time, right, you kind of have to understand that as you think about how you're going to achieve circularity for different materials. So the approach we took to this was to model demand and simulate what we think are expected lifespan estimates for batteries, and then recycling efficiency to determine what the best case scenario is for material recovery. I glossed over a lot of this, but we have to know cathode chemistry over time and over place, because different countries and markets have different preferences for cathode chemistries or battery chemistries. And we have to know something about EV sales and the average battery capacity in each EV that's going out there to really determine the total demand for material and the supply into the market, and then obviously retirements based on how long something will be in use. So this is kind of the headline result from this study, which is that we can under very, very optimal conditions, which are not realistic, we can achieve pretty high circularity potentials even by the year 2040. And you can see here, for example, that cobalt's the highest. That kind of makes sense based on the trends I told you about, where we're trying to design out these problem materials like cobalt, right? This is really great news. This should be kind of exciting, right? Since recycling really matters, right? It really makes a difference. We really need to make sure this is happening. But this particular study was premised on really, 100% collection rates and very high recovery rates, meaning that we assume 100% of end-of-life batteries are collected and that they go to absolutely the best recycling plants you can imagine with respect to recovery of the constituent materials. In reality, that's not what happens, right? We don't collect 100% of batteries, and the recycling facilities don't recover the maximum amount possible from each one of these batteries because of the economics of doing so. So other than trying to get excited about how important recycling is, why do we care about modeling like this? Modeling like this can actually help us inform policy. And one such policy is a recycled content standard, which we'll talk about in a few minutes. Another one might be to think about the role of recycling in meeting global resource demand, or thinking about how much material is really available out there, some of which could be secondary recycled material and some of which would be primary or newly mined material. And the other reason is to think about, well, what else can we get from recycling, right? What are the opportunities for reducing the impact of vehicle electrification? So I'm going to start with that last point. And this is work that Jessica Dunn led, looking at the potential for recycled content standards, but in particular the potential net environmental benefits and cost benefits for recycling. And I'm showing you here the environmental outcomes. What I'm showing you here are the results of a life cycle assessment. And what you see in each one of these is a blue bar that are the emissions from recycling a battery, a green bar, which are avoided emissions. Avoided emissions refer to the idea that when you generate recycled material, you essentially avoid the need to produce a newly mined and refined material. So a lot of folks use the term virgin material. I don't like that word. I'd rather say primary or newly mined material, but that's a common term. The black dots represent the net emissions, meaning that once you account for all the impacts of recycling, what are the net benefits, essentially, or net impacts, but in here they're benefits of recycling. And I'm showing you results for greenhouse gas emissions shown in CO2 equivalent, SOx and NOx emissions. These are both criteria air pollutants that we worry about. And what you can see is that in all cases, we get quite a bit of benefit from recycling. These benefits vary based on what recycling technology we use. And here is shown direct recycling, hydrometallurgical, and pyrometallurgical. Just to define those terms a bit better, and I'm not going to go into the sort of like the technical details about these, but pyrometallurgical plants exist today. But I think of them a bit as like legacy facilities insofar as all new facilities being built are hydrometallurgical. You have the potential to recover more material through hydrometallurgical processing than pyro processing, which is why the benefits were a bit lower for some of the pyro processing. And then finally, direct recycling. This is not really a commercialized technology, but here the idea is that some people call it cathode to cathode recycling, but the idea is that you maintain more of the quality of materials in your battery as you recycle. So instead of taking a battery and getting all the materials out in like the black mass that I showed you, where they're all mixed together and you have to extract and refine them and everything else, you could retain some of all the work that went into refining and combining these materials in the proportions that you want them to be combined in, and save on that. But again, that's not yet commercialized. Okay, so if recycling is so good, right, it delivers on environmental benefits, it avoids the need for mining new materials. Why don't we, we should have laws, right, that say we should do this, right? But the US doesn't have laws in place for this. And like I said, it's purely market driven. That doesn't mean there's no recycling happening. It just means that we aren't necessarily realizing all the potential benefits. And so we can look to other jurisdictions that have actually developed policies. And the two other largest markets for electric vehicles, the European Union and China, both have reasonably comprehensive regulations in place for managing end-of-life EV batteries. But we can look to the EU, which has this sprawling kind of regulation. And by sprawling, I mean that's good. It has tentacles in lots of places. And it's tried to think about the circularity of batteries. So thinking not just about the end of life, but how we make batteries and everything else. And I think of what they've done around EV battery recycling as designing for both pushes and pulls in the legislation. So the push includes things like extended producer responsibility. So the OEM that sells the vehicle with this battery in the first place is responsible for managing it at end of life. And this carries forward what has long been in place in Europe, an end of life vehicle directive. Another push is that you have to, for these responsible producers, they have to show that they are disposing of or recycling these batteries appropriately. And to do that, they have to use registered or eligible recycling facilities. And these facilities have to meet minimum requirements for high rates of recovery for key materials, among other things. And then they also design in a pull. What do I mean by that? I mean that they actually are creating a market for recycled materials. So they have a recycled content standard that requires new batteries in the future to use some minimum fraction of recycled materials, and that minimum fraction kind of grows over time as more recycled content is expected to become available. So this is an example of a kind of a policy that's thought about both pushes and pulls to making sure that recycling happens, and when it happens, high quality recycling is happening, and there's a market for those materials when they're done. So one question we could ask is what recycled content standards could look like here in the US. And the equation here just shows you that the recycled content is going to be based on sort of the amount of recovered material available divided by the current demand for material, right? So it has to reflect sort of the ratio of recycled material to new demand. And that can tell us what a recycled content standard could look like. So the modeling approach, and this modeling was led by Jessica Dunn. The modeling approach taken here is similar to the last modeling approach I showed you, except here you can think about the scope was just the US, not the world. And there was greater focus on thinking about this particular steps for recycling, like collection rates, how many batteries are being repurposed, and the recycling process itself. This repurpose matters because when we take a battery out of a vehicle and then we put it in a new application, we essentially delay its availability to recycle, right? We're saying, no, you're going to take a stop here, you're going to provide more services in this other use, and then you'll eventually go and get recycled. But there's this potentially very long delay. It could be anywhere from 4 to 10 years, right? While it's being repurposed or being used in a new purpose. So with this model, here I'm showing you just reports, the results for maybe the 3 most important materials that we often talk about: cobalt, lithium, and nickel. And you can see that for cobalt and nickel, we can see very high potential rates for recycled content standards out to 2050. Now that's a long way away, but that's 25 years away. If the average age of a vehicle on the road today is over 12.5 years, and the average lifetime of a vehicle is something like 17 years, then you can see why it takes a while for this recycled material to become available and then be used in new batteries. But for nickel and cobalt, we see relatively high levels of recycled content would be viable. For lithium, we see lower levels. And this goes back to that diagram I showed you where we had changing chemistries over time. Even as we just fully get rid of nickel and cobalt, say in an LFP battery, we still need lithium, right? So lithium is the constant in these batteries, whereas these other materials can change. And so that's why we see lithium still has a reasonably low potential for recycled content relative to cobalt and nickel, where we see really high ones. All right, I'm gonna move to repurposing now. So I've already shown you some pictures like this about repurposing, but remember here, the idea is we take out a battery from an end of life. We take out a battery from a vehicle because it's reached its useful life in the vehicle. And that could happen, like I said, because of restrictions on power or range, because that's about how much energy you can store. But that battery might still be in really good condition for a lower demand application, like for stationary storage. I should say, stationary repurposing can come in many forms. What I'm showing you here is a particular way of repurposing where you basically don't touch the insides of the battery. You just overlay a new battery management system and you use them as is. Of course, there are other repurposes that might open up that battery. They might selectively remove modules or cells and remake a battery that's either the same form or a different form, but actually they've actually gone in and done things to the battery. They've touched it before selling it or using it as a repurposed battery. So this is kind of the lowest touch version of repurposing that I'm showing you here. All right, so I'm not sure how many people are familiar with the concept of a waste hierarchy or the waste hierarchy, but this is a concept that the US EPA has used, and the image here is actually from the European Commission. But the idea is that we have a preference for what we do first around waste. The first preference is to prevent it, to not generate waste in the first place. So this might be a use less kind of thing. The second is to reuse or repurpose. So keeping products in their highest value use for as long as possible. And by value, I don't just mean like economic value. I mean the sort of the services that bring most value to the environment, let's say. Okay, and then after that, recycling and recovery, and then ultimately the last thing we want to do is actually dispose of it, like in a landfill or something like that. And the waste hierarchy basically says we should definitely prioritize reuse or repurposing above recycling. But we have a tension here. So I think I pointed out earlier that when we repurpose, we delay the time until a battery can be recycled, and we really need that recycled material. These are some graphs from our earlier work on circularity, showing that the years of second life use, meaning how long a battery is used in a repurposed application, affects circularity. So let's just take a look at nickel here. With 0 years of second life use, we might achieve a little under 60% circularity by 2040. But with 15 years of repurposed use, we're down at like 1 or 2% circularity. And this all has to do with how long batteries are in use and thus not available for recycling. This really changes the picture for how much material we need, right? It's like, oh, maybe we shouldn't be repurposing, maybe we should be recycling. The thing is, there's lots of stuff going on here because when we repurpose, we, in theory, displace demand, right? We say if we don't need a different battery if we have this repurposed battery to do the job. The other thing is that new lithium-ion batteries actually are kind of better. They use less cobalt. They might technically be better, like more energy dense, etc., or more durable. So the question is, should we rush to recycle these old lithium-ion batteries, given that we need this material and that new batteries are essentially better, or should we stop along the way to repurpose them? And so this turned into a research question. Basically, does the waste hierarchy hold given changing lithium-ion battery technology, like chemistry changes and such, and this need for material for new batteries? And we wanted to examine this using environmental, social, and economic impacts, really focusing here on life cycle assessment as a measure of environmental performance. So we considered 2 scenarios, one where a spent EV battery is repurposed in a lower demand application, a stationary storage application, and another where the same service is provided by a newer low cobalt chemistry battery. In all cases, batteries go to be recycled at the end, right? We're assuming everything gets recycled at the end. And we're very careful to make sure that the energy service provided is identical in these 2 systems, right? We want to compare apples to apples. And so after doing that, we did this life cycle assessment, and this was led by Jessica Dunn in partnership as well with another graduate student, Kavian Ritter. What we found here is that repurposed batteries are still much better from an environmental standpoint. And that includes the fact that these batteries are a little bit less efficient. Things like round trip efficiency and charge discharge go down. That's accounted for here. The repurposing process is accounted for. And the fact that you get a big credit for recycling, or bigger credit for recycling at the end because of the higher cobalt content in old batteries. See, this is an NMC 111 compared to newer batteries with lower cobalt content. This paper is great. I encourage anybody interested to read it. I'm not going to go into all the details. Also explored different anode technologies, as anode technologies are changing as well. But the key takeaway here is the waste hierarchy holds true. Even under these conditions, it's still better to repurpose and get as much service out of these batteries as you can, rather than pushing everything directly into recycling. I should point out that there are plenty of retired batteries that are not in a condition to repurpose, right? They may have problems that make them unsafe to operate, or don't operate at all unless there's a whole lot of repair and remanufacturing that may not be worth it, and so forth. So I'm not saying every battery that retires will or should be repurposed, because some of them aren't in a condition to do that, but that for batteries that are in a condition for repurposing, we shouldn't necessarily be pushing them right into recycling right away. We don't want to recycle instead of repurposing, essentially. I already showed a graph that looked a bit like this. I just want to point out, like, repurposing is really exciting. We don't have a lot of retiring batteries yet, like I said before. So we're just at the beginning of this industry and this process and this sort of technology. And I expect that we'll see a great deal happening in the future as we see more and more batteries retire. And we may reach a point where there really isn't the number of retiring EV batteries is going to outstrip demand in the repurposing sector. That's certainly possible in the future. All right, so that was a really fast overview of an immense amount of work and research, but I want to kind of try to summarize things and then think about, I want to summarize everything and then leave a lot of time for Q&A. The first I want to summarize is the qualitative research that really attempted to map out the EV and EV battery end-of-life network and pathways, and learn from the stakeholders in those networks what they saw as the biggest opportunities and risks out there. Along with providing sort of a consensus-based, maybe authoritative mapping of this industry, we also found that there were some common themes that stakeholders expressed. These include issues around safety and cost. And the cost concerns can be related specifically to an industry, but also this idea that we're relying on a market-based system, and that market is really uncertain as technology continues to evolve and change. One thing that a lot of folks point out, and not necessarily in these interviews, is that as we design out cobalt and nickel, for example, that's great. They're high-cost materials. It lowers the initial cost of our batteries, and it potentially has lower environmental impacts. But it also means that the end-of-life battery is worth less, right, for recycling. So we have a lot of change happening, and there's a lot of uncertainty around cost and economics. There's also the revelation of a real commitment to circular battery economy. And one thing to point out is we actually do a pretty good job of recycling vehicles in the US. And it's purely market driven. The challenge is, does that hold as we really, really fundamentally change the technologies that are inside of our cars? And then finally, sort of the reason why this is all really risky in a way is that we don't really have any mechanisms in place for ensuring that batteries are ultimately recycled, or that sort of the waste hierarchy is honored as these vehicles move through end of life, or these batteries move through end of life. In the quantitative modeling work, we used material flow analysis to understand circularity potential, kind of inspired by our global work. We really focused in on the US and thought about using material flow analysis to inform potential future policy, in this case, focusing on a recycled content standard and understanding what opportunities are there to try to require or to build that pull for recycled materials. We also use life cycle assessment to quantify the environmental benefits of recycling, and recycling sort of at economy-wide scales, and that is proof that these are really environmentally beneficial. This is a very environmentally positive approach, right? We're getting a lot of benefits from making sure that we're recycling these batteries. We also looked at sort of answering the question of like, do we repurpose or do we immediately recycle? There's this tension because we're sort of denying the market recycled material if we extend the service life of batteries once they're finished in a vehicle. And even with these tensions, it's clear that it's great to repurpose when you can, and that repurposing delivers real environmental benefits, real environmental benefits, and so we kind of uphold that waste hierarchy that I talked about earlier. So I think it's pretty evident from my talk that we probably need some kind of policy. And right now we do have policies that manage end-of-life batteries, but they are sort of generic. These batteries are considered hazardous waste, so they have to be transported a certain way. They can't be disposed of in a municipal landfill because of their designation as hazardous waste, for example. But there is no real policy. There's no real thinking about how to manage batteries at end of life the way, for example, that the EU has developed. And the EU could provide a pretty good blueprint. There's no way that the EU would generate something that would be exactly what the US needs, but it certainly could provide a blueprint for comprehensive battery end-of-life policy that could be tailored to US conditions. And I want to be clear that there are actions out there right now to try to create EV battery end-of-life policy at the state level, such as here in California, and at the federal level. But these are sort of in nascent stages, and it's exciting to do work that maybe could help, push and provide information that could help design better policies here. All right, so I'm happy to take questions. I want to point out that Meg Slattery is here as well and will be available to answer questions as well.
Thank you so much. And we have a lot of questions here for the last 12 minutes. So I'm just going to jump right in, Alissa, and also Meg, if you'd like to answer as well, please feel free. So we'll start off with how do public safety electricity shutoffs impact keeping EVs charged to provide reliable transportation?
Okay, that is an excellent question. I don't think that our work on end-of-life batteries offers a lot of responses to that. I kind of have two. One, I think that this is convincing people to go fully electric in the face of power shutdowns is clearly a challenge. I don't like anecdote and scientific talks, but I will provide one, which is that I have a family member that lives in reasonably rural Sonoma County and was subjected to multiple very long shutdowns. And she was unwilling to get rid of her plug-in hybrid for a full electric under those conditions until she got a Powerwall. So one answer might be that that people will be more comfortable or more able to adopt fully electric vehicles when we do have more options for essentially like on-site power storage and generation, which could in theory be enabled by some whether it's repurposing of batteries and such. It could enable a system that would work better for folks who have a fear of not being able to charge when they really need to.
Great, thank you. And moving on to the next question, which exact physical and chemical changes does a lithium-ion battery experience as it ages?
Wendy, thank you for that question and for revealing that I am not a battery scientist. And so I can hand a few of those over to Meg maybe, but really there's a lot of things that happen. For example, you get lithiation on your cathodes. You get different kinds of swelling in your battery that can lead to damage and a loss of function. And then you have other kinds of faults that occur in a battery that can really prevent the battery from functioning well. So lots of things happen there. In terms of the outcomes for a battery user, I can talk better to that, which is that you increase resistance, meaning your battery doesn't charge as efficiently and it doesn't discharge as efficiently. you decrease capacity for storing energy, and you decrease the amount of power that the battery can deliver. So that's sort of like the user experience of an aged battery. But the actual chemistry and what's happening inside is not something I can speak to.
Thank you. And let's see here. Do you think consumers and manufacturers are likely to adopt an EV with a reused battery?
That's a great question. I, as a early adopter, wish I could get a used battery into my vehicle if it was in better condition than the one I have, because going 9 miles isn't really worth it, is it? So I think it kind of depends. I think one thing that's on the horizon for our research group is actually a really big focus on repairability for batteries. And so I think that is the next horizon, is making sure that we can repair. This is important for multiple reasons. When we think about most people in the world and most people in the US buy used cars, not new cars, and we rely on repairing in order to keep our vehicles on the road. And now we have the most important and expensive part of our car isn't repairable, essentially. So repairability, I think, is the next big thing. It's the next thing we really have to work on for EVs, and the next thing that we really need to understand better as well.
Alissa, can I chime in on that question?
Mm-hmm.
Also, so I think it is a really great question. One of the key kind of issues that came up around reused and repurposed batteries is around warranty and being able to guarantee the performance of a used battery. And that's partly why I think the importance of having a standardized way of measuring and reporting the state of health of the battery, and then also just as we have batteries around for longer and there's more demonstration of the performance of those used batteries, I think the expectation is that will increase consumer confidence. But it's hard to tell exactly what's going on now, because I think some dealerships report that it's much harder to sell used EVs compared to a comparable internal combustion engine car. But I've kind of heard conflicting things as well about used EVs and used batteries, like getting a higher price at auctions, for example. But I think it is a really important question, both for reused batteries in EVs and repurposed systems. And then the other anecdote that I will throw in there is that I also heard about parents buying used EVs for their teenagers because the range is a little bit lower, and that actually being kind of a benefit for them. And I think it's possible we'll see more of that as the cars have longer ranges, and so a used battery can still take you pretty far compared to some of the earlier models.
Great, thank you. And I'm just sort of going down this list here, and we have quite a few that I'm not sure I don't think we're gonna get through the entirety of them in the last few minutes that we have. So one thing I wanted to request of our speakers is maybe, so we will have a transcript of all of the questions that have been asked, and maybe after the presentation, if you both wouldn't mind kind of responding to them, we can share those with the participants from today, so that they can have a text response if any of their questions aren't answered live. Okay, great. So we have a question about lithium-ion battery safety. Since LIBs deteriorate over time, my understanding is that spontaneous combustion becomes more likely, can be hard to extinguish fires related to this. Let's see. So how are these increased risks being considered in the export of used or aged EVs with LIBs?
This is a great question. I know Meg can speak a bit to the actual fires and issues around that, but I think right now the way that this works is if a used battery is still in the vehicle, it's not considered hazardous waste. So if you put a used EV on a container ship and ship it overseas, for example, it's not considered waste. And so that's an issue. And there has been some work to try to figure out how to do a better job of determining when something's waste and not, even if it's in a vehicle. But right now, there's really no limit on that, especially in the US. And I don't know if I've about the sort of on the export side. I think one of the big opportunities, and we do have some research projects thinking about used EV exports. One of the things we're really thinking about is what kinds of conditions could you put on the export of vehicles? of used electric vehicles. For example, does the battery state of health have to be in some kind of condition? Do we need new approaches to modeling or assuring that batteries are in good condition, a kind of condition assessment of some kind, before we put them on a ship to be transported or before we can sell them into a new market, that sort of thing. So I think, I know that that's a vague answer. The answer is there are no rules right now. And if the battery is still inside the vehicle, it's not considered waste. And so I think there is a lot of work to do there. I think that new laws, like here in California, the ACC2, where it's requiring that EVs have an onboard measure of state of health that a consumer can see, really empowers, whether it's export laws or import restrictions, empowers people to actually be able to at least say, well, we don't want EVs arriving here if the battery state of health is less than 80% or less than 90%. So I think some of the technology and policy changes that are happening will help enable better management for import-export of used vehicles. Meg, I'm not sure if you've got something to add there.
Yeah, I'll just add that there are pretty strict regulations around the packaging for shipping end-of-life batteries. They're considered a hazardous material, and particularly if they're damaged. So they need to be shipped in a special case. So I would say the issue is maybe more around training the new parties who are used to handling combustion engine vehicles around the proper packaging protocol. And so just to make sure that it's done correctly. And I also would just note that it is definitely based on my experiences going to conferences and things. It's definitely an area that the industry is very aware of. And there's a lot of companies that are working on packaging material and safety. So it's kind of another area where it's, we're just kind of trying to, or I feel like I'm just trying to keep up with understanding what they're doing. But it's certainly a big area of concern.
Okay, thank you. And I'm going to steal our last minute just with a quick question. I was wondering if you could just elaborate on some of the work that you've done to help your research impact policy, because there is so much happening right now, like in California with Senate Bill 615. And I can put in the chat for folks a quick description of what this bill is. But this is exactly the type of research that is so important because it's timely and this is happening now. So just really appreciate the work that you and your team are doing, and wondering if you could elaborate on that a bit.
Yeah, I mean, I think because we're just developing policy in this area, I do think that the work we're doing can help inform the bills and regulations that come out, or help motivate different approaches to how policy and regulation is designed. And I think in other work that our research group did in addition or concurrent with NCSD was to provide research support and writing support to the advisory group for the state of California on end-of-life batteries. And I'd like to say that there was a lot of synergy between that project and the research that we do. That project, included stakeholders, and we understood the problems that they saw. We did research on their behalf that inspired new questions. And the sort of a lot of the work that went into that, I think shows up in the policies that we see getting designed now. And again, I think, yeah, this is one of those opportunities where we can be helping to inform what's next, like a recycled content standard, for example, in the US, or other needs out there as well. And I think Meg can also talk maybe a little bit about on some of the work around safety and everything else. I think a lot of people are thinking hard about that now as well.
Mm-hmm. Yeah, I don't have too much to add. Definitely working on the recycling advisory group process was really helpful and rewarding, of kind of seeing the impact and kind of conducting the research in parallel with having policy design. I think that has been a really rewarding experience for me. And I would say we haven't done a lot of this yet, but I think part of making this kind of information usable for policymakers and the stakeholders and the public is thinking about how to put it into more accessible forms. And kind of, I think like one thing that I would be really interested in doing is making a shorter version of the network paper or of those policy recommendations that we came up with during that process, because I think there's a lot of information out there, or there's a lot of information that we have here, and I think we just need to think about how we can make sure it's communicated in a way that's usable.
Yeah, and I'll applaud NCST for making sure that we do webinars, that we do policy briefs, and we get those shorter versions out there. And the other thing to say is, you know, there is movement happening in the U.S. at the federal level as well, and I hope that some of what we've done will help inform what's out there as well. And yeah, that's the best we can hope for, actually, right? That we actually make something happen from our research and it doesn't live in an academic silo.
Awesome. Thank you so much. This was really informative. We are at time, so I'm going to close this out with just a reminder for our participants. Please do fill out the evaluation survey. It's just going to help us keep improving these as time goes on. And we'll also follow up with supplemental materials that'll help just kind of maybe answer some follow-up questions. And then we will also post all of the questions and responses to those as well. So follow-up materials to come. Thank you again for joining us, and thank you to Dr. Kendall and to Meg for joining us. And I hope you all have a wonderful rest of your day.